Okay, so today we're going to take a look at a classic physics problem. It refers to something that is more commonly known as the Atwoods machine. Well, I wouldn't say commonly known. It's not something that you really talk about on a regular basis, but it's a classic physics problem to take a look at. In short, what you end up with is the following. You have a pulley, hopefully one that is low friction and pretty low mass so that it won't actually adjust things very much at all. What we do is we run a rope over it, and we hang two masses. We'll call this one M1, and we'll call this one M2. Now, if M1 equals M2, when we let go of them, they just kind of sit there. We'll double check that among other things, but the other thing that you normally do with an Atwoods machine is you start mixing and matching the masses, where we'll make this one a little bit heavier than this one, and now they'll start to move, and we're looking to try and predict how they're going to move. In short, this has been used quite a bit to actually test the ideas of Newton's laws themselves by applying them onto two different objects that are now interacting with Earth's gravitational field to result in motion, hopefully predictable motion. So I'm going to walk you through how to work with this. There'll be another video, probably right after this in the playlist, so starting, we're going to go through and we're going to do this kind of the very, very thorough way where we do it entirely by the book. And then I'm going to incorporate a few other ideas in another video where I'm going to show you ways that you can look at this a little bit differently and maybe be able to do it a bit faster. Now, I'm not recommending necessarily that you do it that way. It's better to understand it the thorough way. But since I'm getting you prepared, well, this is intended to get my students prepared for the AP exam, a lot of times time can be of the essence. So if there's a way that you can approach it that might make things simpler, that's another way of looking at it. So there'll be a second video for that. And I'm going to try and collect some data, but I still have to get my ladder and run some stuff for this. Anyway, Atwood's machine. So let's actually take a closer look at it. Let's say what we're going to do is we're going to solve this by deriving an equation. We started doing that in class. It's very important for the AP-C exam, and it's getting to be pretty important for the AP-1 exam. On top of that, when we derive an equation, it's going to let us basically solve the Atwoods machine for any combination of masses. So in the work that we put in to solve this once, we kind of solve all of them, or at least all of them that have a pulley with negligible friction and mass. In other words, we're going to say that the rope just kind of goes over that and we don't have to worry about the pulley slowing things down or causing any problems. In real life, they usually do, so we may not get exactly these results, but we should get pretty close if we have a pretty good pulley. Derive an equation for the acceleration or accelerations of our two objects with an Atwoods machine. Now, I want my answer, as he flies, answer in terms of M1, M2, and universal constants. What we mean by that is, for this one, we're going to find, basically it means little g, the acceleration due to gravity near the surface of the Earth. We use the number positive 9.81 meters per second squared, or newtons per kilogram if you'd prefer that, in class. The last one will make more sense after we look at fields and talk about the strength of the gravitational field, which is a bit later in the year. Atwood's machine. All right, let's go through and start solving these. And now you've got an idea of exactly how I would phrase this, or the AP exam would, if we were asking for this sort of thing, which they very well might. So let's see, deriving an equation for the acceleration, answer in terms of M1, M2, and universal constants. We want to predict the motion of these objects. Specifically, we want to find the acceleration. Now, as we talked about in class, there are a couple different ways that we could go about finding accelerations. We could use kinematics. Unfortunately, we're going to need to know things like delta x, initial velocity, final velocity, time. I've got nothing on delta x, and my answer cannot be in terms of just delta x. That's not a universal constant, and it is neither of the masses. So, nor is there time or the velocities inside our equations. So, there's a bit of a hint that we want acceleration, and we're answering in terms of m, but we're actually going to approach this using Newton's laws. We've got two objects, so we're going to set this up where we look at the two different objects. First thing to do, draw free body diagrams, M1 and M2. Okay, so I'm going to draw a free body diagram here for M1. The two forces, well, the forces that I have acting on it are going to be the force of gravity on one and the force of tension. We have tension holding it up from the string, and we have gravity trying to pull it down. If we cut the string, no more tension, and the thing free falls. Over here for mass 2, we have actually something pretty much identical, although it's the force of gravity on mass 2 and the force of tension. Now you'll notice that I'm not giving subscripts to the force of tension, because as we talked about in class, since with our current setup and the mass of the pulley being negligible among other things, that may sound a little confusing. Wait till we get to rotational mechanics. The force of tension might change later on with much more complicated problems. But since our pulley is nice and simple, the force of tension is distributed through this wire, and however much we have pulling up here is the same that we have pulling up here. All right. So these two forces of tension are actually the same. I will point this out. One of the ways that we can kind of simplify this is turning it into a train car problem like the one that we looked at in class. And if you will remember, when we had the two wires connecting them, they had an equal magnitude of the force for each of them. Okay, we have no forces in the x, so this one's actually hopefully pretty simple. After we have our free body diagrams, we apply Newton's second law. So sum of forces equals mass times acceleration. Forces are vectors, so if we're going to add them, we need to do our sum of forces in the x, and that will be equal to our mass times our acceleration in the x, and sum of forces in the y, and that will be equal to our mass times our acceleration in the y. As I mentioned before, we have no forces in the x for either of these, so we're just going to skip over that. It's a whole lot of zeros, so let's do our sum of forces in the y. So there's none in the x, all of our interest is in the y. I'm being a little bit lazy here. I've gotten lazy over the last couple of years. Let's say that to the right is positive x and up is positive y, our standard coordinate system. In the y direction, for mass number 1, we have force of tension, positive because it's up, minus the force of gravity on object 1 equals the mass of object 1 times the acceleration of object 1. Now, we don't know what that acceleration is. That's actually what we're trying to find. We'll do more about that in just a moment, but this is set up for object 1. The one thing that we're assuming right now is that the force of tension here is equal to the force of tension there, because that's more or less what happens with our ropes or strings, especially in these types of problems. Later in rotational mechanics, we might add a little bit to that, but that's when we're paying close attention to a massive and possibly with friction pulley. All right. I'm going to replace the force of gravity with its equation, m1 times g. Remember, the force of gravity near the surface of the Earth is equal to the mass of the object times the acceleration due to gravity, little g. So my mass is m1, and g is, well, g, equals mass 1 times acceleration 1. Great. My problem is I could try solving for the acceleration here, and I'd have it in terms of m1 and g, but I have an ft in there, and ft was not one of the things that I can answer in terms of, so I'm not done yet. On the upside, I have another thing that I can take a look at. If I take a look at this one, my sum of forces in the y equals my mass times my acceleration in the y. Well, that's going to be ft for this one, minus the force of gravity on object 2 equals mass 2 times the acceleration of object 2. It's going to look very, very similar to what we have here. Let's see, so putting these side by side, we've got the force of tension minus mass 2 times the acceleration due to gravity equals mass 2 times the acceleration of object 2. Now, one thing that I will bring up, I've been kind of lazy in how I'm doing this, but technically, these accelerations are still vectors. We talked about that in class. These forces are vectors too. I put them in the y direction, we have positive and we have negative. Now, the reason that I bring up the vector on this is because there's one little trick that if you forget on this problem, it'll throw things off. And I don't mean to call it a trick to make it sound like we're trying to get you. It's a subtlety that you have to pay attention to. And if you don't pay attention to it, then the equations don't work out. I made a big deal about Newton's second law saying that we have vectors and we're looking at how these vectors interact. We can't just ignore that we have vectors over here. All right, so here's what I'm going to do. I've got two of them that are helping me out here, but I need to get rid of the force of tension, so that's what I'm going to do. What I'm going to do is I'm going to add this over, and we're going to say that the force of tension equals mass 1 times acceleration 1, plus, I'm adding this over to the other side, m1g. Now, g is not a vector. I mentioned that in class. I said it's always positive, and that when we talk about g, it's actually the magnitude. The force was a vector, and we kept track of that by having negative. Do not, I repeat, do not put negative on the 9.81. I've told you multiple times in class, and I will remind you here, when we use g, it is always positive because we keep track of our direction when we work with our forces. It's a common mistake, and that is why I'm emphasizing it. All right, well, if this is our force of tension, I can plug it in over here. And I get the following. Let me bring that back up just a smidge. We're going to have the force of tension, that's mass 1 times acceleration 1, plus mass 1 times g, minus, so this is the force of tension, I'm replacing it there, force of tension, minus m2g equals m2a2. Great. Here's where I'm going to bring in something important, and this is where we want to take a look at it, why I set you up for the accelerations. When I let go of these, if they go anywhere, well, let's say, for instance, that mass 1 is heavier than mass 2. So they're going to go like this. The acceleration of object 1 would be downward, and so a1 would be less than 0 because it's going to be a negative number because the acceleration would be downward. If the acceleration of m1 is downward, well, which way is m2 going to accelerate? Well, since they're tied together, this one has to accelerate upward, and just like we talked about in class with the train car problems, they're stuck together, so they will have the same magnitude of the acceleration. In this case, a2 would be greater than 0 because it is accelerating upward. Now, if instead m2 were greater, then we'd reverse this. a2 would be down and less than 0, but a1 would be up and greater than 0. In short, no matter what setup we have the following relationship. a1 will be equal to negative a2. Or you could say negative a1 is equal to positive a2 because of their directions. This may seem a little weird, but the acceleration is a vector, and we need to keep track of that. So when we set up that these two are related to one another, they have the same magnitude, they're the same number, but one of them is down and one of them is up. We need to keep track of that. So that means that if I were putting in numbers, a1 and a2 would be the same number, but one of them would have a negative on it. We don't know which one because it depends on which one's heavier, if either of them are heavier. So here's what I'm going to do. I'm going to use that a1 is equal to negative a2, and I'm going to do the following. m1, let's say, let's go ahead and put this one in. It'll be fine. Negative a2. Now I'm going to drop the vector sign on there. I put it back in there to remind you that the acceleration is a vector. And that was so you know that while these two have the same number, one of them is up and one of them is down, and we need to incorporate that. We already did it with the force side of the equation. Forces are vectors, accelerations are vectors. We kept track of the force side because we had positive ft and minus fg. So the forces have already kept track of their direction. It's the accelerations that we need to put a little bit more into. Whenever you have something accelerating downward, technically we're going to have a negative for that acceleration because it is still a vector. All right, enough of that. Let's go through. Plus m1g minus m2g equals m2a2. And honestly, at this point, now that I've done the replacement, those are just the acceleration. They both have the same magnitude of acceleration. The directions that each of them move is going to be dependent on which one is heavier, for instance. All right. But we can solve for a2, for instance. All right, so here's what I'm going to do. I'm going to expand this out a little bit. We have negative M1 A2 plus M1G minus M2G equals M2 A2. Now, we want to solve for the acceleration. So, all of the math that I'll be doing at this point will be to try and get acceleration equals some stuff. So I want to get the accelerations together. Well, there's an acceleration over here, so I'm going to add this over to the other side. We get M1G minus M2G equals M2A2 plus, this is negative, and I add it over, M1A2. I can now factor out the acceleration. We get M1G minus M2G equals M2 plus M1 times A2, the acceleration of object 2. All right. Well, I want acceleration equals some stuff, so why don't I just divide M2 plus M1? I'm going to end up with the following. A2 equals M1G minus M2G divided by M2 plus M1. Now I'm going to do one final thing. I can factor the G out here. I'm going to get it set up in what I'm used to seeing, and this will actually tie into the next video that we take a look at. G times M1 plus M2 divided by M2 plus, minus, pay close attention, Sanchez, there, minus M1 minus M2 divided by M2 plus M1. Here's our acceleration, technically for the second object, but let's check a few things. First off, we've just finished deriving an equation, and one of the things that I've been telling you all in class, one of the best ways after all of this mess of algebra to double check that you can even remotely be right is to check your units. Well, acceleration will be in meters per second squared equals, this will be meters per second squared, times kilogram plus kilogram, so that's just going to be kilogram on top, divided by, kilogram minus kilogram, but we'll have a number in kilograms, divided by kilogram plus kilogram, that's kilogram. Ooh. Hey, our units do work out. Here's another thing that we can do. We can check something called boundary conditions. In other words, we're going to check kind of the edges of things. So we've got an equation that looks like this. The acceleration of object 2, which will be the acceleration of object 1, it's just one of them goes one way and the other goes the other, so I could actually drop the subscript. But let's go with G times M1 minus M2 over M2 plus M1. Let's check something. What happens if M1 equals M2? I mentioned that at the very beginning. If we have both of these identical, we hang them there and we let go of them, what do? What's going to be their acceleration? Well, logic would tell us that it's just going to sit there if they're both the same mass. So let's put that in. So if M1 equals M2, I can then plug it back into my equation and see if it gives me an acceleration of 0. Well, let's see. My acceleration would then be equal to G times M1 minus M2, but remember, M1 is equal to M2, so M2 could be written as M1, because they're both the same, over M1 plus M1. I suppose I should write M1. Great. Well, anything minus itself is 0. 0 divided by a number is 0, and 0 times g is, hey, look at that. Our acceleration does come up with 0 meters per second squared. We check that boundary condition. Awesome. What if, let's go to another extreme. What if we have a mass here, m1, but we put something so laughably tiny here, it's a negligible mass? Or, phrased differently, what if I don't put a mass on there at all? In short, what's the acceleration of these things if m2 equals 0? It is so small compared to m1 that it's like 0.003 kilograms, whereas m1 is 1,000 kilograms. Something where one is just so much bigger than the other that it's almost like the other thing isn't there. We'll approximate it to 0. What do we get? G times m1 minus 0, because we said m2 was going to be either so tiny or just not even there. Imagine we didn't hook anything there. And that will be 0 plus m1. Well, that just comes up to g times m1 over m1. Hey! The acceleration would be equal to g. This object, if m2 was nothing, we didn't put anything there, this would just free fall. It would fall and have an acceleration equal to that of the acceleration due to gravity, because it's basically just falling. This is ignoring any effects from the string. As I mentioned, I may not have said anything about the string, but the string and the pulley are basically just really, really light and small and not affecting this. All right, this is how we check some boundary conditions. This is really good to do if you can for any of the equations you derive as well. All right, so in the end, we've now found and double-checked that the acceleration, at least the magnitude of it, will be equal to g times mass 1 minus mass 2 divided by mass 1 plus mass 2, or mass 2 plus mass 1. With addition, order doesn't matter. Now, we may also have m2 minus m1, and we'll get a negative. In short, that's setting up where if we were being extra specific, one of them will be positive and one of them will be negative, mainly because, again, whenever we put different masses on here, one of them goes up and one of them goes down, and it depends on which one is bigger. In short, what we're actually looking for is the magnitude of the acceleration, and so we take the magnitude of this. We're just trying to find the number. All right, that is the Atwoods machine and how you develop this.